Why study linear algebra today? See, the modern world, it runs on data, and linear algebra is the math of data. If we talk about linear algebra, it is the math of data. Linear algebra provides the essential language for representing multidimensional information and the computational framework for processing data at scale. So now it's very clear to us that in the modern world, we are dealing with the data and we need some mathematical tools so that we can efficiently handle that data. We can represent that data. We can process that data in an efficient manner. And linear algebra is that tool. So linear algebra is that tool using which we can represent multi-dimensional information. And linear algebra, it also provides us the computational framework for processing data at scale. So now we are getting or we are realizing the significance of linear algebra, especially how it is a perfect tool in dealing with data, in processing data, in managing data. So every major technology today, it depends on linear algebra. So any major technology you take, it has something to do with the linear algebra. Like if I talk about artificial intelligence, machine learning, deep learning, so these all, they make use of linear algebra. So artificial intelligence, machine learning, deep learning. So linear algebra is the bedrock of artificial intelligence, machine learning, deep learning. And linear algebra, it is used from data storage to actual learning process. So in the field of AI, ML, and deep learning, we use linear algebra to represent the data. We use it for data representation. So all the different forms of data, like the images, text, audio, it is converted into vectors, that is the list of features, and matrices, that is the data sets for computers to process. So in AI, ML, and deep learning, whatever the data we have, that data can be the text data, textual data, images, audio, we convert that data into vectors and matrices, and then we compute it. So, if we are talking about vectors and matrices, we are talking about linear algebra. So linear algebra is used for data representation in AI, ML, and deep learning. And similarly, linear algebra is used for model training. So in neural networks, learning involves repeatedly multiplying input vectors by large weight matrices. And that multiplication of input vectors by large weight matrices is carried out using the principles of linear algebra. And hence, linear algebra plays a role in model training. So the idea is that we have a data, like the input data, we have the weight matrix. Now using the principles of linear algebra, we multiply the data, the input vector with the weight matrix to get some prediction vector. So we carry out the matrix multiplication, which is a concept of linear algebra. Linear algebra, it is also used in AI, ML, and deep learning for optimization. So optimization is like minimizing the cost function, minimizing the error. So techniques like gradient descent, it uses linear algebra to adjust weights, minimizing errors, and improving the model accuracy. So now it's very clear that in the field of artificial intelligence, machine learning, and deep learning, linear algebra plays a very, very important role. Linear algebra is used to represent the data, whether you are dealing with the textual data, you're dealing with images, or you're dealing with audio. We convert those data into vectors and matrices before further processing it. So linear algebra has a role to play in data representation. In the field of AI, machine learning, and deep learning, linear algebra plays a role in model training. So we have like we multiply the input vector with the weight matrices. So that matrix multiplication is taken care by the principles, the concepts of linear algebra. And also linear algebra also plays a role in optimization. Like in AI, ML, and deep learning, we use gradient descent as one of the optimization technique. And that gradient uses gradient descent, it makes use of linear algebra to adjust weights, minimize errors, and improve the model accuracy. So linear algebra, it also plays a role in recommendation systems and search engines. So linear algebra is used in recommendation systems and search engines. So modern web platforms, they rely on matrix operations to organize the internet and predict what you will like. So in search engines, matrix operations are used. In recommendation systems, operations are used. So if we talk about search engines, and in search engine also, uh, we are mainly emphasizing on the page rank. So in search engines, especially the page rank, Google, it represents the web as a massive adjacency matrix where links between pages are entries. So companies like Google, like we all use Google search. So Google search, it represents the web as a massive adjacency matrix wherein the entries of these matrices is the link between these web pages. So finding the most important pages is mathematically equivalent to finding the dominant eigenvector of this matrix. So Google search or any search engine you consider, if we are talking about the page rank algorithm of Google search, it makes use of the adjacency matrix to represent the web pages. So the entries of adjacency matrix is the links. So wherever there is a link between the web pages, that will be an entry in the adjacency matrix. And we find the most important pages mathematically using the linear algebra, using the concept of eigenvector. We find the eigenvector of this adjacency matrix, which will give us the most important pages. And hence we are making use of linear algebra here. Similarly, in recommendation systems also, we make use of linear algebra. So recommendation systems, you know that we have seen recommendation engines like any e-commerce platform. If you visit, it recommends you some products. If you explore an OTT platform like Netflix, it recommends you movies. If you visit LinkedIn, it will recommend you connections to follow. So that is what recommendation engine is. So in recommendation systems, like services like the Netflix, it uses collaborative filtering. So companies like or the products like the Netflix OTT platform which we use, it makes use of the collaborative filtering, which involves factorizing a large user item matrix into small feature matrices to predict missing ratings. So this is called as matrix factorization. So basically in collaborative filtering, Netflix, what it does is that it uses the user item matrix, like based on the past behavior of the user, what items the user preferred. So making use of the user item matrix, it factorizes a large user item matrix into two smaller feature matrices. So these are like the feature matrices. So we have a matrix called user feature and an item feature. So a large user item matrix is factorized into a user feature matrix, a smaller user feature matrix, and a smaller item features to predict the missing ratings. And here also we are making use of matrices, and hence we are making use of linear algebra. So now we are realizing the importance of linear algebra, that linear algebra not only in artificial intelligence but also In recommendation systems and search engines, linear algebra plays a very big role. Similarly, linear algebra do play a role in computer vision and robotics. In computer vision and robotics, linear algebra plays a very big role. So, computer vision and robotics, they use linear algebra to translate physical word geometry into digital coordinates. So, if I talk about computer vision in particular, so in computer vision, digital images are stored as matrices of pixel values. So, in computer vision, we represent digital images as matrices of pixel values. Operations like the edge detection, blurring, or rotating are performed by applying linear transformations, that is a matrix multiplication, to these pixels. So the operations on the image is basically the linear transformations of these matrices. So the idea is that in computer vision, we represent digital images as matrices, like we represent it as a pixel matrix, a matrix containing the pixels, and the operations on these images like the edge detection, blurring and rotating is basically the linear transformations on these pixel matrices. So hence computer vision heavily makes use of linear algebra, because whenever we are talking about matrices, we are talking about linear transformations, we are talking about linear algebra. So linear algebra is used to represent digital images and also to process digital images. Similarly, in robotics, if we talk about robotics, in robotics, engineers they use homogeneous transformation matrices to model a robot's pose, that is a position and orientation. So the modeling of a pose of a robot is done using homogeneous transformation matrices, which is a concept of linear algebra. Even like solving inverse kinematics, like calculating how joints must move to reach a specific point, is a complex system of linear equations. So in inverse kinematics also, it involves complex systems of linear equations, which is a part of linear algebra. So now it's very clear that if we talk about linear algebra, it has applications in computer vision and robotics. In computer vision, we represent digital images in the form of matrices, pixel matrices, and processing of image is basically the linear transformations performed on the pixel matrices. Similarly, in robotics, we use homogeneous transformation matrices to model a robot's pose, and to solve inverse kinematics, we make use of complex systems of linear equations, which is a part of linear algebra. So linear algebra, it also has a role to play in scientific computing, signal processing, and beyond. So linear algebra do have a role to play in scientific computing, signal processing, and beyond. So linear algebra provides the heavy lifting for complex simulations and data analysis. So we talk about scientific computing, if we talk about scientific computing, so linear algebra plays a role in simulating physical phenomena. So simulating physical phenomena like the weather, fluid dynamics, it requires solving millions of simultaneous linear equations, often using LU or QR decomposition for efficiency. And which are the concepts of linear algebra? So linear algebra, it is used in scientific computing. So when we are simulating physical phenomena like the fluid dynamics, weather, it requires solving millions of simultaneous linear equations. And to solve those millions of simultaneous linear equations, we make use of the concepts of linear algebra like the LU or QR decompositions. Linear algebra also has a role to play in signal processing. So in signal processing, techniques like the fast Fourier transforms, which is also used in Wi-Fi and audio compression, are rooted in linear transformations that convert signals between time and frequency domains. So, if we talk about signal processing, in signal processing, converting the time domain into the frequency domain and vice versa is very important. So, the fast Fourier transforms, they make use of linear transformations, which is a concept of linear algebra. So, linear algebra do play a role in signal processing also. So, the fast Fourier transforms, like conversion from a time domain to frequency domain, it makes use of linear transformations. And linear algebra also plays a role in dimensionality reduction. So principal component analysis, it uses eigenvalues and eigenvectors to compress high dimensional data, keeping only the most important features. So the idea is that, let us suppose we have some high dimensional data. Now using the principal component analysis, like which makes use of the eigenvalues and the eigenvectors, so we can reduce the dimension. So, so dimensionality reduction we can do using the principal component analysis, which further makes use of eigenvalues and eigenvectors, which is a concept of linear algebra. So now it's very clear to us that, okay, if we talk about scientific computing, signal processing, and beyond, like dimensionality reduction, linear algebra plays a role. In scientific computing, like if we are simulating physical processes, it involves solving millions of simultaneous linear equations. We make use of the concepts of linear algebra, like the LU or the QR decompositions. In signal processing, we do the conversion of the time domain to the frequency domain. We make use of something called as fast Fourier transforms. It uses linear transformations, which is a part of linear algebra. And also in dimensional reduction, we make use of principal component analysis, which uses eigenvalues and eigenvectors to compress high dimensional data into important features. So this eigenvalues and eigenvectors is a concept of linear algebra.